take it.
Okay, thank you very much. Thank you for coming back. So today we'll have the second lecture on the Swampland program. And before starting, let me summarize a bit what is the main message that we learned yesterday. So yesterday we started discussing, after this long introduction about what the Swampland is, the absence of global symmetries in quantum gravity. Okay, so this is one of the most important Swampland conjectures, which is motivated by string theory examples, as I tried to show, and we'll see today also what is the evidence we have for it, more general evidence. And the statement basically is that symmetries, I mean, if you have any exact symmetry in the theory, it should be gauged. Okay, so we try to explain what does it mean to be gauged, like what is the difference between being global and being gauged. And I try to give like some intuitive explanation in terms of whether you can measure this symmetry from very far away or not. Now, this was just some intuition, so this was one slide of yesterday, so you don't need to copy it again. Just to be clear that, I mean, there is a proper way, I mean, there is a well-defined way to distinguish these global symmetries from gauged symmetries. And this was the definition that we gave yesterday for what a symmetry is, which was given in terms of some topological operator that was satisfying these conditions. So let me just summarize the important things. So the point is that we had this topological operator that is topological in the sense that it's a symmetry, so that the stress, it commutes with the stress energy tensor, it is invariant under smooth deformation. And it has it acts non-trivially on something, okay? So there is some charge operator. Now, we discussed the case of the scalar field, okay? Where these are the operators, and here, let me remark that what happened when the symmetry is gauged, no? When we couple the scalar to a gauge field, is that the operator that is charged under the symmetry is not gauge invariant anymore. Okay, so what happened when we are gauging the symmetries is that this second condition fails. Okay, so this operator is not gauge invariant because it's not invariant under the shift transformation of the scalar. You need to combine it with a transformation of the gauge field. And then this condition here fails. So there are no gauge invariant charge operators under the symmetry. And that's why if the symmetry is gauged, it's not part of this definition of a global symmetry. Okay, so violated if gauged. I mean, obviously the first one fails if the symmetry is broken, because then it's not gonna be topological, it's not going to commute with the Hamiltonian. Okay. And that's the statement that there are no global symmetries in quantum gravity means that you need to violate one or the other. Okay, one of these two conditions. Okay, so there was also, I wanted to say this because there was one question which I wanted to postpone for the end to have time to discuss it, but actually then at the end I forgot. So sorry for that. And it was, so I'm just gonna say it now because otherwise I will forget again. So there was the question of why these higher force symmetries are always abelian. And let me just give the quick answer before I forget again. Of course, we can discuss more about it later. But since the symmetries are characterized, right, by these operators that live on these higher dimensional manifolds, a 0-4 global symmetry is supported on a codimension 1 manifold, no, a d-1, so that it can be non-abelian in the sense that when it's non-abelian, right, the different operators will not commute with each other. And if it's just a codimension 1, I mean, maybe, right, you cannot deform one to the other without crossing and so on. But if we have a higher force symmetry, the manifold in which it's supported has a lower dimension, so a higher codimension. So you can deform one into another at different times. And I mean, you have enough dimensions to play with, right? So the group necessarily has to be abelian because you can always deform one of these operators at a given time to another operator in a different time. Okay, so it's just a matter of the dimension that you have a line in space-time, and right, like in 4 dimensions, you can just move it around and doesn't need to cross another line necessarily. Okay, this was the quick answer that I wanted to say yesterday after the talk, but then I forgot. So I hope it's more clear. And then the plan for today is that we are going to give.
Can I ask a question about that answer?
Yes, please.
What about zero-form symmetries that are non-abelian? How do you see those geometrically?
It's not necessary. I mean, the point is that it's not necessary that you don't have to commute. It's just that it's non-trivial. It's not obvious. Okay. They have, right? So that depends now on the correlators. Like you have to study correlators and see whether they commute or not. Okay. But there is no way to make it non-abelian if it's higher form. That's the point.
All right, thanks.
Okay. Is there any other question from yesterday? Okay, so this is the plan for today. Now that we understand hopefully a bit better what is global versus gauged, we can try to give more general evidence for this conjecture. So I will start telling you what is the evidence that we have, what are the general proofs that have appeared. Then I will say a few words about this generalization of no global symmetries in terms of co-ordination classes, because it's also becoming quite important in the past few years. And finally, we will discuss what happens if the global symmetry is not completely exact, but it's approximate, like we break it a bit or we ungauge it a bit. And how should we think about that? Because if there are no exact global symmetries in quantum gravity, something wrong has to happen when you try to engineer one, when you try to make an approximate symmetry very, very approximate, no? Very almost exact. So this will be useful to introduce this second notion that is very important in the Swampland approach, which is the fact that when we try to engineer these global symmetries, we get this infinite tower of states that become light, and the cutoff of the EFT is always lower than the Planck mass and lower than what you would expect from naive EFT expectations, okay, like from QFT. This will be the main points that I hope to convey today, that sometimes the EFTs break down earlier than what we would expect. Okay. So let's go for the evidence. So yesterday I put you already this slide that there are like 4 points I want to discuss. We briefly talk a bit about some heuristic arguments that we have in terms of black holes. We will discuss more about black holes tomorrow. So tomorrow I will give, when we will discuss the weak gravity conjecture, and then we will discuss all these general arguments based on black holes and how this problem, this trouble with remnants gets solved if we have a gauge symmetry instead of a global symmetry. But still there might be some problem if the gauge coupling is too small. Okay, so this is something we'll see tomorrow. So black holes for tomorrow. And today, I want to focus on these other 2 mainly. Okay, so let's move this. And let me remind everyone that if you have any question, please don't hesitate to interrupt me. Okay, so the fact that there are no global symmetries, especially if we are talking about continuous symmetries, is something very old. You can already find it in the book of Polchinski for string perturbative theory. And for continuous ones, or string perturbative theory, let me see, these 2 options, the message is more or less the same. So the message is that whenever you have a global symmetry in the worldsheet or in the boundary CFT, this corresponds to a gauge symmetry in the spacetime or in the bulk, respectively. Okay, so we have a global symmetry in the worldsheet or in the CFT. We are talking about 3D CFT. This corresponds to a gauge symmetry in a space-time or in the bulk. Okay, so that's, I mean, global symmetry is something physical that even if we have different dual description of the same thing, we should have the same type of global symmetry, something that cannot disappear under dualities, which is, it contrasts with the case of gauge symmetries, which are just redundancies and they are not fundamental and they can disappear. So if we have some global symmetry in CFT, we should have some sort of global symmetry in the bulk. And what one can show for the continuous case is that it's just a gauged global symmetry, okay? So there's no way to have a global, a purely global symmetry in space-time. Now, why is this? It's actually just one line if you want to do it in ADS-CFT. I mean, probably last week or the previous one as well, you learned that in ADS-CFT there is correspondence, right? We have a dictionary between operators. This is a CFT operator, a primary operator in the boundary, and bulk fields, right, in ADS. So this is a bulk field. So for any bulk field constructed from the vacuum, you get a CFT operator, and you can map the conformal dimensions to the mass of the field, the bulk, and so on. And the point is that if we have some gauge field in the bulk, this gets mapped to some operator, dimension d-1 and spin 1, which is a conserved current in the boundary. And especially what is important for us is that any conserved current that you have in the boundary, any global symmetry that you have, corresponds to a gauge field, okay, in ADS. Okay, so it's I mean, I want to say it's simple, but like the intuition is this. Of course, the most complicated thing is to be able to prove this in general, even if you don't have a conserved current. Okay, so for that reason, there is this also nice, more recent work of Harlow and Oguri, in which they have more general proof based on entanglement wedge reconstruction that is valid for symmetries that are splittable, at least in the boundary, even if they don't have a current. Okay, so it's something that can apply also to discrete symmetries as long as they are splittable. So what I'm going to do is to explain you a little bit what this proof is, even if we will not get into the hard details of this entanglement wedge reconstruction. Okay, any question? Okay, so let's consider we have, okay, let's make this a bit nicer, some ADS-CFT. Perfect, nice. So the basic idea of this entanglement wedge reconstruction is that we can divide the boundary into different subregions, okay? Such that for every subregion in this boundary, let's call this Ri, we can construct some extremal surface, which is what I painted here, such that any bulk operator localized inside this extremal surface, so any bulk operator, let's call this omega r, can be represented the CFT as an operator localized in this subregion of the boundary. Okay, this is the basic idea. This is what is called entanglement wedge reconstruction. Of course, there are many more things you can say about this and try to understand exactly how to construct these surfaces and so on. But for that, it's not very important. Just believe me right now that you can construct these surfaces. And what is important is that if the global symmetry is splittable, which means that, so when we have a splittable symmetry, global symmetry is splittable, then we can split, as the name indicates, the action of this symmetry. So we have this is the topological operator describing the symmetry. So we can split it as a product. So let me do it the other way around, actually. As a product of operators localized at the different regions. Okay, so if we do that, if this symmetry has this property, which will have it if it has a conserved current, but can be more general than that, then we can get a contradiction for having a global symmetry in the bulk. Because imagine now that we have some operator here, some bulk operator that is charged under the symmetry. Okay. Now, we can always choose these surfaces to be very small, such that they don't, the operator is not localized in any of them, so that there is no way to reconstruct this bulk operator from the boundary. So that this operator, which in principle was charged under the symmetry, commutes with all the symmetry operators localized at the different subregions. And this is a contradiction because in principle, I mean, we should have some charge operator under the symmetry in order to be a symmetry. But if all of them commute, then there is no operator in the boundary that is charged. So there is no global symmetry. So it's a contradiction because then it seems that we have a global symmetry in the bulk, but we don't have it in the boundary, and that cannot happen. Okay. And this is a contradiction.
Question.
Yes.
Why did you choose the regions to be very small?
You can do it. It's just that you have the, I mean, you can choose the subregions as small as you wish, such that you will end up with some contradiction, even if the operator has some finite extension in the bulk. So precisely because you can do it, then, I mean, this is a problem. Okay. So the resolution of this is to be able to transfer this information from the operator localized in the middle of the bulk to the boundary in some way. So it's like this notion that we need to be able to measure this from far away. And how do we do that? Well, we can gauge the symmetry, because if we gauge the symmetry, then there's a Wilson line that will be attached to this global operator. I mean, we can have a Wilson line attached that ends on the boundary, and therefore will cross one of these surfaces necessarily. And then we can access to that information and reconstruct the charge operator from the boundary perspective. So this happens if it's.
That's a question.
Yes.
Thank you. It's I think a follow-up on India's question, which is, it seems here that you took very small subregions, and then you have an operator in the center that commutes with all the operators in each subregion. But like if you do that generally with any operator, that will always be true. And isn't that a statement about code subspace versus about the code subspace, so that it commutes with any operator in that small region? So it seems like, how physical is this construction? How is it true that if these commutators are true when you take this specific partition of the boundary, then that just means that you cannot have any global symmetry?
That's the idea. Yeah, I mean, the idea is that this would be a contradiction in ADS-CFT, right? I mean, because you should be able to describe any bulk operator. I mean, you should be able to represent it as reconstruct it some way, even if it's in a non-local way, but you should be able to reconstruct it in the boundary. So if you find some procedure which does not, I mean, if you find setup in which you cannot do that, it means that the setup that you started with is inconsistent, right?
But isn't it true that if you partition the boundary in this way, you cannot reconstruct any operator of any kind in the center?
No, because in general, as I said, like for example, if the symmetry is caged, it means that you will have Wilson lines that can end on the boundary. And then it's like to transfer this information there. So you can construct, I mean, in fact, all the operators we have in area CFT are always of this type because we don't have, I mean, there's no example of global symmetry in quantum gravity or in the bulk of ADS. So all the operators that we always reconstruct is thanks to this type of thing that we can insert something that like some caged Wilson line or some extended object.
Okay, I understand this. I think I wasn't probably clear on my question, sorry. So what I mean is, entanglement wedge reconstruction tells you that if you have a region of the boundary you shoot in your tangent surface, you can reconstruct everything and only what is inside the entanglement wedge, right? So if you partition the boundary in this specific way, and so your entanglement wedges do not cover the whole bulk, then in general, okay, if you have an operator charge under some particular symmetry and you dress it to the boundary, then you can reconstruct it. But it seems like in general, if you have an entanglement wedge construction where you do not cover the center of the bulk, in that specific code subspace, you cannot reconstruct the center of the bulk unless you have to consider like larger regions on the boundary. Isn't that true in general?
I think you're asking why the resolution of this is that it's wrong to have these small subregions. No, like why you cannot take that perspective. And this is more about the proof of this entanglement wedge reconstruction and how you construct these extremal surfaces and how small they can be. I mean, there are different proofs, evidence for this, because in the end, it's like locality of the CFT, what allows you to do this. And I don't see any way in which it could be consistent to do it for large subregions, but not small ones. I mean, I think that's there is no loophole in that sense. But but this is, I mean, I want to remark that this is the only case in which one gets trouble. I mean, when we have these global symmetries, because it's the only type of thing that we cannot really extract from far away. You can take a look. There are nice references, like in the paper of Harlow and Oguri. They have nice references about the proofs that we have for this entanglement wedge reconstruction idea. So maybe, I would recommend you to look at because maybe, to see all the subletics.
Thank you very much.
Does this work if your ADS has multiple disconnected asymptotic boundaries?
Multiple disconnected asymptotic boundaries. You mean like, for example, if you have like some factorized CFT?
Just a wormhole topology.
No, I think, also that's okay. Actually, there are also arguments, not exactly that, but you can play a lot also with these wormholes and like double field theory, double thermal state, to show also that you need to have these charge states and that the Wilson lines will be able to break and you have charge states and so on. And they also appear here in the paper of Harlow and Oguri. I think precisely for this statement would be fine. Here, I have to say, it's very clear that this works also if you have like just some weakly coupled ADS to one and you just have one stress energy tensor, because then you don't have any of these subletics. But in principle, as far as I know, all these, I mean, this proof and this entanglement thing works in general, just based on locality of the CFT. But you can take a look at the paper and then we can also discuss maybe on Friday about these things in more detail. Any other question?
Yeah, I have a very naive question. So when arguing the reconstructability of the bulk, we have a similar paradox saying that you have your bulk operator and boundary operator are like commuting because they're like spatially separated. And the solution in that case is that actually your TOSA space is like much smaller than like the physical Hilbert space or cold Hilbert space is much smaller than the actual Hilbert space, the CFD. So why can't we use that? Like, I'm just wondering, like, what's the difference, like, for this argument and like in that paradox? Why can't we use that paradox to say maybe you need to go to like higher energy space, Hilbert space to actually reconstruct the operator of like Colville symmetry?
Honestly, I'm not sure how to give a good answer to that. I think it's true that there are some subtleties, like for example, there's one subtlety that I avoided also, which is that when you split this into a product in the different subregions, you can also have things located at the edges. And it's not completely obvious if you could try to reconstruct it that way. But I don't know. I mean, this is like a modern approach, and there are many discussions involved. So maybe you can put this. I mean, I would recommend all of you that you can put it in the Slack, and we can try to discuss among all of us what are these subtleties, and try to point, if there could be any loophole or not. And also it will be easier for me also if I see it written to see exactly what you have in mind. So let's postpone it to the Slack, okay?
Yeah.
But yeah, I mean, this is great. I think this is precisely, so this is the point, okay, guys? We have to try to think how, we have to be critical and try to think of all these explanations. And especially if you're working in the CFT, I mean, probably you know about these things, so you can try to connect it with your background and the things you know. And if we generate some discussion and interactions from this, and we can continue in the Slack, it's fantastic. Okay. Okay, good. So this was all I wanted to say about the area CFT. So the next point before we finish all this universe of global symmetries is to say a few words about coordination classes. Okay, so well, maybe before that, let me summarize just then what is the evidence. So we have these works, for the splittable symmetries. We are discussing to what extent just comes from the locality of the CFT. And then, as I said, tomorrow we'll discuss about the black holes. And let me also point out that there are these works I'm not going to discuss because I would need several lectures also to explain everything here. So there are recent works also connecting this absence of global symmetries to having a unitary black hole evaporation. So all the recent developments of the page curve that probably you have learned in the past weeks with the black hole information paradox and so on. All these new developments are also show the absence of global symmetries. And people have argued that that if you have a theory with unitary black hole evaporation, it should not be possible to have global symmetries. And more concretely, you can see that all these replica wormholes that I'm not sure if you have seen in the lectures, but I mean, they are part of the modern derivation of the page curve. They are going to violate these global symmetries. Okay. So more generally, what happens is that when you have topology changing processes in quantum gravity, these processes, like these replica wormholes and other things, can violate the symmetries, which opens a new way also to think about this, which is that probably what is wrong is to pretend to have some topological operator in quantum gravity. Okay, so when we study classical Einstein relativity, general relativity, we learn that geometry is not something fundamental, right? So it doesn't make sense anymore to pretend that things are not going to change, under in space and time and so on. So geometry can change, and we know gravity can change the geometry. right? We have some planet, changes the geometry around and so on. And the next step is that when gravity is quantum, when we have quantum gravity, not even topology is fundamental. So you can also change the topology. Okay, we have processes in string theory which change topology of the space. And that means that it's probably not well defined, doesn't make sense to have some topological operator, which is the same as having a global symmetry. Okay, so that's why that's completely fine in quantum field theory, because in quantum field theory, you start with a theory in a given topology and that's it. But in quantum gravity, topology fluctuates. So this is just a message that I wanted to throw here, because probably making this more concrete and sharpen this intuition could help a lot in the future, and maybe this progress comes from some of you thinking about these issues. Okay. So topology itself fluctuates in quantum gravity, so maybe there are no topological operators. Okay, so there are no topological invariants.
Question.
Yes.
How is quantum gravity different from a topological quantum field theory in this context? I mean, topology changing or topology fluctuation is also something that you would expect in a topological quantum field theory. So what is extra about quantum gravity?
No, right. It depends. So how would you define? Okay. So it's about, if you imagine that you have some path integral, right? The question is, you have to sum over different topologies or not? No?
I mean, topological QFT is also defined without reference to any background, right?
Yeah, but I don't mean, okay, there are different levels here, right? It's not just a matter of background independence, or, I mean, the point is that in the definition, right, in quantum field theory, we define some path integral and we don't sum over different topologies. In quantum gravity, now one of the things that is also under debate, but it seems we have to do, is that we need to sum on the path integral over different topologies, and these are also very important, no, in the unitary page curves, summing over all the different wormholes and so on. And I think this is something very specific of quantum gravity, which is not even in topological field theories.
Yeah, thank you.
More comments? Of course, I mean, I'm happy if people want to make a comment or have a discussion, feel free to do it. Okay. Okay. So, following this idea that maybe there are no topological invariants, we can generalize this even more to the statement that they are not even covered in class. Okay. So, what does this mean? Let me explain a little bit. So, cobordism, okay, let me first explain what this word means. Is the statement, okay, so it's an equivalence relation. So that if we have two manifolds, let's call it CD D of a D-dimensional manifold, they are, let me put it here. They are bordant, okay, cobordant to each other. So they are on the same class, okay, of cobordism group. If their union can be seen as the boundary of a manifold with one dimension more. So that is a way to connect these two manifolds. Okay. Now, this is a mathematical concept, but the point is that it's very useful in order to define what are topological charges in general, like not just involving gauge fields that maybe we know how to define, but also topological charges coming from gravity itself. Okay, so you can think that the different cobordism classes, so if we cannot connect some manifolds with others, they correspond to different types of topological global charges. Okay, so there is something that distinguishes them, and that prevents you, that it's an abstraction to be able to glue them by another manifold of one dimension more. So the conjecture that Jake here and Kumbrun formulated is that, this is a conjecture, all cobordism classes in quantum gravity must vanish, in the sense that everything should be connected to each other. Because otherwise, they give rise to a d minus t minus 1 form global symmetry, where this is the total space-time dimension, this is the internal space. And this is a global symmetry characterized by charges given by these non-trivial cobordism classes. Okay. So if you want to avoid all these types of possible topological global charges that you could imagine to have in quantum gravity, you need to require that that this Bordism group is trivial. Okay. So you have non-trivial global charges, and this can have a lot of implications for the effective field theories. So if I think that I'm compactifying string theory on these manifolds, what happens is that here I get some effective field theory, okay, coming from compactifying string theory on these compact manifolds C, and I get another effective field theory coming from compactifying string theory in this dimension, this compact manifold D, and the existence of this cobordism, of this correlation, is seen as a domain wall interpolating between the two effective field theories. Okay, so in general, the way to understand this conjecture is that any effective field theory of the same dimension should be connected by a finite energy domain wall. Okay, so that all EFTs of same dimension are connected by finite energy domain walls. Okay, now this is actually I think the proper way to think about the conjecture, because in general it's very hard to even compute what is this cobordism group of quantum gravity, because we know how to compute it in specific examples that you can have like an approximation of it because we have some compact manifold, we know the ingredients that we have and you can compute it. But the point is that the way to understand this is that you should always have enough ingredients in your quantum gravity theory, enough defects, such that this cobordism group is 0, which means that if you compute one, at some point you compute this mathematically, which is well defined and you can do it, and you obtain that it's non-zero, it should tell you that you are missing something. Okay, so you should always have something that trivializes this group, such that all the effective field theories that you get are connected to each other. Okay. Any question? Okay, this can seem a bit exotic, but I think it's nice at least to put you the idea of what it means, because I'm sure it will continue to appear in the next years. And it could be that it's it's kind of the modern approach that we are starting to think about the absence of global symmetries. So let me give some examples and make a few more comments, and then we just change to the last topic of the day. So if everything belongs to the trivial class, okay, so here I'm saying that two manifolds are on the same class, no, if they are connected by another manifold of one dimension more. But if the group is trivial, it means that everything should belong to the trivial class. And the trivial class means that a manifold is a boundary by itself. Okay, so that if we have some manifold C, you can shrink it, and it's the boundary of another manifold of one dimension more. So that when we compactify string theory on this compact manifold, okay, so we have string theory on CD, we get some EFT, this EFT. And the fact that it belongs to the trivial class, the fact that I can shrink this manifold here to a point and there is nothing behind, can be seen from the effective field theory as what is called an end of the world brane. Okay, and this is very cool. I don't know, I really like it because when you have an end of the world brane, it could also happen that it's energetically favorable for this end of the world brane to expand. And if that happens, if the end of the world brane expands, which can happen if you break supersymmetry and so on, then it yields what we call a bubble of nothing instability. So I'm not sure if any of you have ever heard of this, but the point is that it's a perfectly well-defined solution of Einstein gravity to have a bubble in which there is nothing inside and just expands and mediates vacuum decay to nothing. Okay, so this is possible as long as indeed there is a compact manifold which is shrinking to zero size at the wall of the bubble. So it's precisely when we have in extra dimensions, no? We have some string theory compactification, and we can shrink these extra dimensions that we can generate this bubble of nothing that will expand if some energy conditions are violated. And the fact that now, I mean, this coverdising conjecture tells you that the this coverdising group is zero, it implies that there is no topological obstruction to have these instabilities. So it's something very peculiar of quantum gravity, and could be correlated to the fact that it's so hard to get stable non-supersymmetry pathway in string theory. Okay, so this is just a comment, but it's nice because it connects this absence of global symmetries with the possible instability of our own vacuum. And maybe by understanding this better and understanding exactly what are the energy conditions that we have to violate and what is the interplay with supersymmetry, we can even give a bound on the scale of supersymmetry breaking, try to answer the question of whether we need to have supersymmetry in our universe or not. So supersymmetry was always formulated, right? So for the naturalness issues, for the electroweak hierarchy problem, like to avoid all these loop corrections for the Higgs mass and so on. But it could be that is necessary for the stability of our vacuum. It could be, this is something that you can try to avoid in quantum field theory because you can write any model you wish and there's no problem. But in quantum gravity, not everything goes. It might be that indeed supersymmetry at some scale is somehow required, and would be nice to explicitly try to find out with that scale. Okay, so this is an avenue in which maybe any of you wants to think in the future about. Any questions? Okay, so just to finish this, yes, please.
So can you give an example where it's not a trivial class? which has a domain wall?
Yeah, so for example, so if you have some, actually, let me give some example. So if you have some compactification with fluxes, okay, some internal space, and you have some gauge fields, no, living on these internal dimensions, you would get that you have different classes given by the possible values of this of the integral of the flux. So let me give, for example, if you have internal fluxes, you can have different charges, no? Which are the integral of the gauge field over the compactification manifold. And if I take D to be the dimension of the internal manifold, this implies that omega D is C. So you have different integral charges that would characterize, no, different effective field theories. And you can have now a boundary, right, like domain walls among them, between them, which precisely describe the jump of these fluxes. So, and actually, like, for example, that would be, if you compute, imagine that you start with the string theory and you only have fluxes and you don't have branes. This conjecture would tell you that, okay, something should go wrong because, I mean, you are missing something because this covariance group is non-zero. And what you are missing is precisely the existence of branes. So to get omega D equals 0, you need to have branes that interpolate between all these flux vacua. Okay, so that this topological charge is not conserved anymore. Okay, this is one typical example. This is a well-known example. Sometimes you can use this also to predict new defects that are not known. Okay, like for example, an exotic example is that in 10 dimensions, like in type 2b or type 2a, I mean, you can consider, well, in general, you can consider what is the covariance group of omega 0. This is C, which means that we need to have some domain wall, for example, in type 2a or in type 2b. And in type 2a is known, I mean, we have O8. So an O8 is also an example of this end of the wall brane. Okay. But in type 2b, there is no object that we know of that plays the role of this end of the wall. Okay. And it's very, and if there is any, it has to be non-supersymmetric. Okay. So if this is what corresponds to a domain wall interpolating between type 2a and type 2b in 10 dimensions, it's predicted by the absence of these topological global charges, these symmetries, but it's not known from a string theory perspective yet because it's completely non-supersymmetric. And also, well, there are many difficulties to try to engineer this because we are interpolating between a chiral and a non-chiral theory. Okay. So yeah, it can be used to predict new defects.
Can I ask also, maybe this is sort of related to that, but what would be an example of something you could do in string theory to falsify this conjecture?
So yeah, so the thing is, when they predict supersymmetric states, in general, we already know, we know them. And when they predict non-supersymmetric stuff, it's in general quite difficult, no? to obtain them from a worksheet or another perspective. Now, there are some corners in which it's still possible try to use this to predict new defects and then try to find evidence for those defects by using anomaly inflow and other techniques. And I know there are ongoing projects about it, which you precisely, like for example, F theory on different compactifications, you can try to study all these covariance groups, what are the defects that they would imply, and study anomaly inflow on those defects, and gather evidence for them using different techniques. So that ongoing projects, that hopefully will appear soon about that. Apart from that, like this is more like an example based, no? Like try to predict one defect and then try to find evidence for it, which is also very nice because it opens a new avenue to understand new ingredients in string theory. Apart from this, like to prove incomplete generality, I don't know what would be the way. I think it's very related to all these notions of what is, and try to define a precise way what is forbidden in quantum gravity, in the sense of topological operators or covariation classes and so on. So maybe in the future, I know there is some avenue, but right now I cannot see any. Yeah. Any other question? But yeah, I think the best way right now is to combine it with anomalies and this type of things and try to show that they have to be there. Okay, so this is it for the global symmetries. So for the rest of the time today, we are going to discuss a bit about approximate global symmetries. Okay, so this is very nice. I mean, like we have all these arguments. I mean, this is a field which is quickly evolving. So that's why I think it's a fantastic moment to be a student and start learning about these things, because our understanding is evolving every year and there are many things to be done. But okay, so in the end, one of the goals is try to connect with phenomenology. And in phenomenology, I mean, it's very important to understand what happens if the symmetry is approximate, right? Because if it's broken, I mean, if you cannot have exact symmetries, maybe there's always some way to go around it, in the sense of saying that the symmetry will be broken at a high energy scale. But if we can really try to quantify how much we have to break the symmetry and how approximate it can be, this would be super useful for phenomenology. Okay. So, in principle, I mean, even if we imagine, let's consider now for a moment that, okay, let's buy that there are no global symmetries in quantum gravity. What happens if I try to engineer one? So, for example, I can take some gauge coupling that goes to 0. Okay. And this is basically like ungauging the symmetry, so that this is going to restore a U1 global symmetry if I just have one gauge field. So there should be some mechanism for which quantum gravity does not allow you to do this. Okay. Now, changing the parameters in a given effective field theory maps in string theory to changing the scalar fields. Okay, so in general, all the parameters are parameterized by the vacuum expectation value of scalar fields, which means that we can move the modular space. Okay, so we can sending the gauge coupling to 0 is like moving in the modular space, or parameter space is like the field space. And then what happens when we try to take one of these limits in which we would restore a global symmetry is that these points happen to be at infinite distance. So quantum gravity pushes these points to be at infinite distance in this modular space, so at the boundaries, okay, of what is allowed. So global symmetries can only be restored at infinite distance in field space. Now, what I'm going to show you today, tomorrow, is that it's not only that they happen at infinite distance, but also that as we approach these points, the effective field theory is breaking down. Okay, so in the end, I mean, if we are here in the middle, we can have effective field theories. We know that if we go to the infinite distance, there is no effective field theory that could make sense coming from quantum gravity. But there is a continuous way in which you can see how this breakdown occurs. Okay, so the EFT breaks down when approaching these points, meaning that there is the cutoff of the effective field theory. So this is lambda, so the cutoff goes to 0. This doesn't go to 0. Okay. As we send the fields to infinity or the gauge couplings to 0 and so on. Okay, so the effective field theory breaks down in a continuous way, such that the better, the more approximate the symmetry is, the closer to being exact, the lower is the cutoff of the effective field theory. And this occurs, as I will show you, because there is an infinite tower of states that is becoming light. Okay. Now remember that we are talking about effective field theories that are weakly coupled to Einstein gravity, which means that we cannot have infinitely many fields weakly coupled to Einstein gravity. One way to see it is that the Planck mass to get renormalized by all these fields, and then in the end, the cutoff goes to 0. Okay, so the tower signals like a drastic breakdown of the EFT, and the mass of the tower is this cutoff. And what I'm going to try to show you is that this cutoff, in all the string theory examples we know, and which is also motivated by black holes, goes linearly, goes with the gauge coupling, so that if the gauge coupling goes to 0, the cutoff goes to 0, or in terms of the field, of the scalar fields, goes exponentially in terms of the field distance. Okay, so this goes to 0 when we take these limits. And that's how the EFT breaks down. And I think this is, we'll see examples, and from a string theory perspective, it's actually very natural, and sometimes it's so natural that people think it's obvious and don't pay much attention to it. But from an effective field theory perspective, it's amazing, because this really goes against quantum field theory expectations. So this is telling you that if you have a weakly coupled gauge theory, in which in principle you control everything and you have quantitative control, if this gauge coupling is very small, the cutoff of the theory is small as well. And you cannot describe, like if this gauge coupling is very small, you cannot describe some process with an energy that is bigger than G and Planck. Okay. And it's purely quantum gravitational, because there is no problem at all from a quantum field theory to do this. Okay. And the same for the field range. In principle, in an effective field theory, as long as the energies are below the cutoff, nothing goes wrong. In principle, from a quantum field theory perspective, there is no problem. But the expectation that all you need to require is that the energies are below the cutoff is wrong. It's not true. There is a correlation between the cutoff in energy and other quantities, such that if the field range, for example, is very large, even if all the energies are below the cutoff, still the effective field theory is going to break down at some point. Okay. So this is I think this is one of the main messages of the Swampland. And from this, using this, understanding this infinite tower of states, how they appear, why they have to be there, and extrapolating this to other situations, is how most of the older Swampland conjectures have been proposed and have appeared. Okay, so it's based on all these towers of states that are, even when you have gauge theories or when you have large field variations. Okay, any question? Okay, so what I'm going to do in the last 15 minutes is to show you evidence for having this tower.
Sorry.
Yes.
Question regarding the last slide. all this putting the lambda similar to as a function of GYM, this is just for a string theory expectation. So it's not a generic EFT or a generic quantum gravity expectation.
So there are two sides here. So first, I want to show you the string theory expectation. So we are going to see, we are going to take many of these limits and see that this always happens and you get these towers of states. And it's purely like string theory based on examples. And then, especially for this one, okay, not so clear for the other, there are also bottom-up explanations of why it has to be based on black hole physics and higher derivative corrections of black hole physics, positivity bounds, and other things.
Okay.
So it's not obvious. I mean, you need to have black holes or more complicated positivity bounds, but you can give general explanations for that. And this is what we will discuss tomorrow. I mean, what is the bottom-up explanation for this?
Thank you.
Any other question? Okay, so how exactly this happened? It's actually, I mean, here I gave like this general notion, okay, that there are these towers of states. In practice, it's encoded in two conjectures. Don't worry about copying this because tomorrow we will discuss this conjecture in detail, so I will go through them carefully. I just want, right now, I just want to, I mean, at least to tell you that the fact that the cutoff goes with the gauge coupling or exponential in the distance is part of these two famous important conjectures, which are the weak gravity conjecture and the distance conjecture. And this is what I reply now, that tomorrow, okay, we'll see this part. So tomorrow we'll see that there is a way to make this more quantitative and not just have order gauge coupling, but to give an order one factor and to fix this in a sharp way using black holes. Okay. But today I just want to focus on what is the universal pattern given by the two conjectures, which is the fact that we get towers of states becoming massless as a gauge coupling goes to 0 or a geodesic distance in field space goes to infinity. Okay, and the cutoff of the theory is given by the mass of this tower. Okay, this is like the universal pattern that we observe, which is encoded in the weak gravity conjecture for the case of gauge fields, or in the case of the distance conjecture when we are just talking about having a large field variation, okay, that we will get towers of states when the field distance goes to infinity. Okay, so as I said, let me forget about the proper definitions. We will see this tomorrow. I'll just focus, sorry, I want to take this one. Yeah. Focus on this part here, okay? For the rest of the day today. Okay, any other question? Okay, so let me give you some examples, which can also be useful for you to understand a few things about string theory. It's nice that actually you will learn a few of these things also later by Natalie, because there is a lot of connection between these towers of states and dualities in string theory. So let's give some examples to get an intuition of what these towers typically are. And as I said, tomorrow we will look for more bottom-up general explanations of this phenomena. Okay, so the first example is that we can start with type 2A string theories. It's a supersymmetric, it's a superstring theory in 10 dimensions. So that the Lagrangian, this is the supergravity Lagrangian. Probably Natalie will also write this later. I'm not sure. So we have I wrote part of it yesterday, but let me go more slowly today. So this is the Einstein term, right? We have the metric, we have the dilaton. So in string theory, we have GS. So this is the string coupling, no? That parameterizes interactions. This is the 10D dilaton. Then we have the Nevers-Vars gauge field strength. And as you see, the gauge couplings are parameterized by powers of the dilaton. And this is a Ramon-Ramon. Okay, this is Ramon-Ramon, and this is Nevers-Vars gauge field strength. So H3 is like the stereo derivative of the B field, and this is also field strength, okay, of the Ramon-Ramon C1. And I have other Ramon-Ramon fields, but now I'm not, we don't need to care about it. So let me just write this action. And here, this is a very simple moduli space in the sense that we just have one scalar field. Okay, so in order to write the geodesic distance, I mean, we need to go to the canonically normalized field. So this is like the integral, right, of the metric for this dilaton, and this is just 1 over the square root of log s. Okay, so this is the metric, right? Since it goes as 1 over s squared, you take the square root, you integrate, and you get the logarithm. Okay, so there are two limits that you can take here. The weak coupling limit and the strong coupling limit. So I guess here, maybe there are people that don't know much about it, so I hope you will learn it this way. And there are people that probably you have seen this many, many times, but maybe this brings a new angle to think about the first things that you learned when you studied string theory. So the weak coupling limit, in principle, I mean, what I am telling you is that whenever we go to infinite distance, so this is going to happen when s goes to infinity or to 0, so that when gs goes to infinity or to 0, we should get towers of states that become light. Okay, and here, well, these tower of states indeed are string modes, right? When the string coupling goes to 0, we get strings that become tensionless, and all the string excitations become light. So the string scale in type 2A is given in terms of the Planck mass and the string coupling this way, so that if we replace it in terms of the canonically normalized distance, indeed, it behaves exponentially. Okay. Now, these towers of states also go with the gauge coupling, right? So the strings are charged under the Nevers-Vars field. So the gauge coupling of B2, we can just read it from this action that I wrote here. So it goes as GS 1/2, which means that the tension of the object, which is the string scale square, indeed behaves as the gauge coupling, as we would expect from the BPS. Okay, so here we see a confirmation again, like these tower of states imply a cutoff that goes exponentially on the distance and linearly on the gauge coupling. And we know what is the resolution. I mean, when you get these towers of states, the effective field theory is going to break down, but string theory takes care of it. I mean, it's not an Einstein gravity theory anymore. Quantum field theory doesn't work anymore. And what would you get in this limit is pure string theory, right? This is the string perturbative type 2A. So you could think that you have some supergravity effective field theory action, and the resolution is to go to the string perturbative limit. Okay. Okay, so this is something that we'll find all the time. Whenever we go to some limit, we get these towers. And in the case of strong coupling, what happens now is that we have D branes that are charged under the Ramon-Ramon fields. Okay, in particular, we have D0 branes that are charged under the C1. And these D0 branes go to zero, the mass goes to zero when the string coupling goes to infinity. So you can compute this carefully, write it in terms of the Planck mass. Let me remark, it's very important here that I'm writing the axiom in Einstein frame, okay? So all these Swampland conjectures are always in Einstein frame, in the sense that it's in terms of the Planck mass, okay? So whatever is in front of the Einstein gravity term must be a constant. And then I write all the masses, no, in terms of this Planck mass, because we are comparing everything with respect to the Planck mass. So that's when the Planck mass goes to infinity, then there is no point to say that they become masses. It's always the ratio between the mass and the Planck mass, what goes to zero. Okay,
Irene,
so yes.
you have just a few minutes left.
Perfect. Okay, thank you. Okay, so these zero branes become massless. This is the specific rate. And again, of course, the gauge coupling of C1, with what you can read here from the axiom, goes as 1 over ds to the 3/4 and scales as the mass of the tower. And what happens now? Well, again, there is a way in which string theory takes care of this. Whenever we get these towers, it means that there is some theory, some quantum gravity theory that emerges. And what happens now is that this is well known to be a decompactification limit in which we go to M theory. Okay, so that's why I say like these towers of states are very natural, because all these towers of states, if you go to the limits and study what the towers are, they give you information about what are the possible quantum gravity theories that you can have. And you can connect them by moving in this moduli space. Okay. Okay. So maybe can I have 1 more minute?
Sure, go ahead.
Okay, so 1 more minute, and then this way we finish 10-dimensional string theory. So there is another very well-known, there are other limits that you can take, which are also easy to understand, which are circle compactification, like Kaluza-Klein compactification. I wanted to mention it also to connect with Natalie's explained yesterday. So this is, if we compactify in a circle, and we go quick, we get a lower dimensional theory, which we have the Einstein term. We have a scalar field, no, which parameterizes the size of the circle, and we get a KK photon. Okay, so the radius of the circle, this is the radius, is given in terms of this scalar field, which I already normalized canonically. Okay, and this alpha is the factor that appears here in the gauge kinetic function. Okay, so just to finish, again, there are 2 limits you can take. You can send the radius to infinity or the radius to 0. And then you get, if the radius goes to infinity, you get KK modes, right? That go to 0 when the radius becomes large. So this is the general formula for the KK modes for any dimension. And indeed, this goes exponentially, right, in terms of the canonically normalized field. Okay, and again, the mass goes as the gauge coupling under the KK photon. Okay. Okay, so this is the compactification, and just to finish, the other one is going to 0. And this is very interesting, because in quantum field theory, I mean, you already have these KK modes, like you compactify quantum field theory, you get KK modes when the radius becomes large. But if the radius becomes small, you don't get towers of states. in quantum field theory. However, if you start from string theory, there are winding modes coming from strings, right, that are wrapping this circle that become light. So you need to have extended objects so that they can become light when the circle goes to 0. And this is, I think, what you saw yesterday as well from a perspective of the worksheet, that indeed the mass for these winding modes is correlated to the mass of the Kecky modes if we change the radius of the circle by 1 over the radius. So there is this limit is also the compactification limit for a theory that has a radius which is 1 over the radius of the original theory. And this is what is behind the duality. And again, it gives you information about what are the possible quantum gravity theories that you can have in the different limits. Okay, so I'm gonna finish with this. So we'll see tomorrow some more examples, but let me just finish with this idea that in the end, the fact that we have this infinite number of states becoming light is nothing else than the manifestation of the different string dualities that are so important in string theory. And the different limits and the different factors are associated with the possible dualities that you can have. So like, trying to understand why these towers are there is trying to understand why we have all these dualities. There might be just redundancies of the theory, but the point, what we always observe, is that when you take one of these extreme limits, then necessarily a new weakly coupled description has to appear. So effective field theories are only valid for finite regions of the moduli space. Okay, sorry if I ran out a bit of time. Let's see if there is any other question.
Thank you. All right. Questions for Irene? Anyone?
I guess I did have a question.
Go ahead.
Okay, sorry. I guess I was just wondering if I'm seeing this right, that if we try to holomorphically extend everything, then there'll be some different twist operators, right, between all the connection points. But is that where the factorization goes next? Is there a clear analog on the string theory end where the topology factors nicely?
So I'm not sure I understand what you mean. You mean like here when talking about the towers, or before?
Yeah, I guess on the hand, what I'm seeing on these towers is I'm seeing a holomorphically decreasing function mapping to the holomorphic dual, and so that just screams that there's a twist operator on two copies of the same state somewhere. But it's more complex because it's a two-way and it's not just a flat theory. But
yeah, it's more complex. I guess you say this also because of all these dualities or relations, no, that we have between the different towers and so on. It's not always known what are the dualities that will be involved, and we'll see tomorrow that when we go to lower dimensions and like more involved compactifications, it's not completely obvious how to interconnect, no? What is the map between all these towers. But in 10-dimensional string theory, it's very simple, so it works that way.
Great. Any other questions?
I have a question. What would be the statement of the cobordism conjecture for any non-geometric compactification of string theory?
Yeah, so I mean, it's true that it's easier to approximate, like you have to think of this quantum gravity cobordism, some object that we need to understand how to define better. It's easier to approximate it, no, with the mathematical cobordism group when we have a geometric compactification and so on. And it's not obvious at all, I mean, how to think of it in complete generality. I think the easiest way, at least for me, to think about it is really from the EFT perspective, that somehow you should have a domain wall interpolating between the different theories. even if they come from a non-geometric compactification or maybe not even internal dimensions, I don't know, whatever happens. So somehow there should be some way to connect all possible effective field theories that you have in a given dimension. Maybe in the future there are better ways to, I don't know, to extend this mathematical notion. I mean, I think this is also, I mean, sometimes developments in string theory come together with developments in mathematics. This might be one of these cases in which the things are going together. How to understand better these objects at the quantum level.
But are you saying that there's a well-defined notion without the space-time or not?
No, well-defined depends on what you mean with well-defined. I mean, there is an intuitive notion in the sense that all EFTs should be connected by finite energy domain walls. It's not a well-defined notion of how to compute, I mean, how to properly define the object, you know, that would be sensitive to the possible topological global charges. In complete generality, I mean, like we know how to do it in given compactifications, but the point is that it's like if, I mean, the way I understand it is that you have this quantum gravity object, which should be something of quantum gravity, including all possible ingredients that you would need to make quantum gravity consistent. And then you have like low energy approximations that work very well when you have supergravity actions and geometric compactification. So like the low energy approximation is this mathematical well-defined notion of coordination.
And that lives on some fixed space-time. It can be dynamically evolving, but it's a fixed.
Yeah, exactly. Yeah, it's like given some, you have to, exactly, you have some dimension. It's like you specify the dimension and you specify also what structure you have. Like you have some spin structure, or you have some fluxes, or like you need to specify what is the structure, and then that's fixed. And actually, I mean, it cannot be the full story. It's like the low energy approximation because it's not even invariant under duality. So it's not like it cannot be the full thing. Yeah. It's like we need, this would be like the classical notion, and we need somehow to understand how to define this the more quantum level, if any.
So when you have these dualities, you can pick any representative and see if it's coordinate to another.
Yeah, exactly. In practice, you can, as I said, like in practice, you say, okay, I have a compactification of this number of dimensions, and I want to have fermions, so I'm going to put some spin structure, and maybe I want to have fluxes, so I need to take into account the bundles associated with fluxes, and then there is a well-defined object that you can compute, and you can compute what is the solution there, and it's typically like in supergravity actions. I mean, like it's like including all the ingredients that we use for the low energy description of string theory. And sometimes it's enough, like already with the low energy description of supergravity, string theory, we can see that these groups are vanished. I mean, and that's it. But sometimes it's not enough in the sense that it's telling us that this low energy description is not capturing the full thing. And how to capture the full thing and take into account all these UV defects involve, more refined notion that is not known yet.
I see, but there's a sense that there's a precise statement and we're saying an approximate version of it, but the statement is not just applicable in this limit. It extends, it's just we don't know how to extend it because we don't have the right language. Is that the expectation?
We have the thing is that we don't know. Okay, so the mathematical notion, which is like the approximation of this notion of quantum gravity coordination, is well defined. Like you can compute this coordination group, but you have to specify the structure. So it's like you have to give as an input what is the structure of your quantum gravity theory. And could be that, I mean, the problem is that we don't know in general what are all the possible things that you would have in a quantum gravity theory. So that's why once you have a concrete setup, you know what things you have, you can compute these things. But in complete generality, I mean, what are all the possible structures that we can have in quantum gravity? Well, I don't know.
Okay.
I think that's
good. Fair enough. Thank you. Okay, other questions? I have monopolized long enough. All right, so then we can end the recorded part. So thanks.